Linear least squares is what we do when matrix A times x equals B has no exact solution. But we still need the least embarrassing approximation. The usual situation is more equations than unknowns. That is not a bug. It is the universe refusing to line up perfectly for our spreadsheet. Given matrix A and B, the least squares problem asks for the vector x hat that minimizes the length of matrix A times x minus b. We often minimize the square instead. Same minimizer, less square roots. A rare case where avoiding roots improves civilization. The key geometric idea is simple. Every vector of the form matrix A times x lives inside the column space of matrix A. So we are looking for the point in that column space closest to B. But we already proved the closest point is the orthogonal projection. The winning matrix A times x is the projection of B onto the column space of matrix A. So least squares is not magic. It is projection with matrix notation. Because apparently every idea needs a disguise. Let R be the residual. B minus matrix A times x hat. At the closest point, this residual is perpendicular to the column space. Being perpendicular to the whole column space means being perpendicular to every column of matrix A. Stack those dot products into one matrix equation, and the normal equations appear. Not summoned, derived. A pleasant change. Normal equations explain the geometry. But QR usually gives the cleaner algorithm. We did all that orthonormal work for a reason. Allegedly. If matrix A equals QR, and Q has orthonormal columns, then the column space of matrix A is the column space of Q. Projection becomes QQ transpose B. Because Q has orthonormal columns, the least squares problem reduces to solving R x hat equals Q transpose B. R is triangular, so back substitution does the grunt work. For a tiny example, fit a line y equals c plus mt through the 3 points 0, 1, 1, 2, and 2, 2. This becomes matrix A times cm approximately equals B. 3 equations. 2 unknowns. The system is overdetermined, because reality enjoys being inconvenient. Gram-Schmidt on the two columns of matrix A gives Q1 and Q2. The corresponding upper triangular matrix is R, and Q transpose B is easy to compute. Solving the triangular system gives M equals 1/2 and C equals 7/6. So the least squares line is y hat equals 7/6 plus 1/2 t. Least squares asks for the closest possible matrix A times x to B. That is the minimization problem. Orthogonal projection explains why the answer is the projection of B onto the column space of matrix A. QR decomposition turns that geometry into a clean triangular computation.